In this lesson, you will learn about permutations and combinations. The first thing I'd like to review is factorials. When you're given a number with an exclamation point next to it, in this case n, it's read n factorial. And what it means is that if you had 3 factorial, that you would take 3 and multiply it all the way until you get to 1. So 3 times 2 times 1 is equal to 6. So just multiply it in consecutive descending order and stop when you get to 1. So 5 factorial would be 5 times 4 times 3 times 2 times 1, and if you multiply these numbers together, you would get 120. For 1 factorial, since you just have a 1, the answer is just 1. And 0 factorial, by definition, is equal to 1. So if you ever have a 0 factorial, the answer is always equal to 1 by definition. So a permutation is an arrangement of objects where order is important. So before we get to when to use the permutation formula, first let's figure out how to use it. So if you have NPR, it's equal to n factorial over n minus r factorial. The numbers n and r could be equal, but your r could never be greater than your n. So if you have 5p3, that's the same as 5 factorial over the difference between 5 and 3, which is 2 factorial. So to figure this out, 5 factorial is 5 times 4 times 3 times 2 times 1, but I'm going to stop at 2 and write factorial because this cancels with this. So the answer to this is just 5 times 4 times 3, which is equal to 60. So for 10p7, this is 10 factorial. I start with the number on the left and then divide it by the difference between 10 and 7, which is 3 factorial. And starting with 10 factorial, I'm going to write 10 times 9 all the way down and stop at 3 because that's the denominator. So I just write 3 factorial. I could write 3 times 2 times 1, but it's really not necessary because the 3 factorials cancel. So I'm left with 10 times 9 all the way down to 4. And if I multiply all of these numbers together, I get 604,800. For 4p0, I start with the 4, so I have 4 factorial over the difference. So if I take 4 minus 0, 4 minus 0 is just equal to 4. So I could write this out, but anything over itself is equal to 1. So 4p0 is equal to 1. If I had 4p4, I start with the number on the left, your n, which is 4, and then I subtract the two numbers. 4 minus 4 is 0, and we know by definition that 4 times 3 times 2 times 1 is 4 factorial, and that 0 factorial is equal to 1. So the 1's cancel, and we're just left with 4 times 3 times 2, which is equal to 24. So that's how you calculate a permutation. So later on, we'll look at when we use a permutation. The next formula I'd like to look at is a combination. And a combination is a selection of objects where order is not important. So the formula is read NCR. So these two numbers, n and r, could be the same, but your r could never be greater than n. So the extra part to this formula is this r factorial. So going right to an example, 5C3, I start with my n, which is 5. So I have 5 factorial, and I divide it by r factorial, which is 3, and then I multiply it by the difference between those two numbers, which is 2 factorial. So I expand the numerator of 5 factorial and stop when I get to 3 factorial, and I leave my 3 factorial, the larger one, so that these cancel. And I'm left with 5 times 4 over 2 times 1, which is 20 over 2, is equal to 10. So always expand your numerator and stop at the larger number that's in the denominator. So for 10C7, we start with our left number, our n, 10 factorial, and we divide it by the r, which is 7, so 7 factorial. Then we subtract 10 and 7, which is 3 factorial, and we expand the numerator, and we're going to stop at 7 because 7 is the larger number in the denominator. So I leave the 7 as 7 factorial, but expand the smaller one so that the 7 factorials cancel, and I have 10 times 9 times 8 over 3 times 2 times 1. And what you could do here is you could multiply 10 times 9 times 8 and divide it by 3 times 2 times 1, but this 2 times 1 cancels with the 8 and makes it a 4, and this 3 cancels with the 9 to make it a 3. So a simpler calculation would be 10 times 3 times 4, which is 120. So for 4C4, we start with our n, the left number, which is 4, and then we divide it by the right number, our r, so another 4 factorial, and then we take the difference, which is 0 factorial. And the 4 factorials cancel, so we're left with 1 in the numerator, and then 0 factorial, by definition, is equal to 1. So 4C4 is equal to 1. For 4C0, we start with our n, which is 4, and we divide it by our r, which is 0, and then we subtract the 2. 4 minus 0 is 4, and this is the same exact answer as the previous one. The 4's cancel, so we're left with a 1 in the numerator. 0 factorial is 1, so our answer is 1. So let's just scroll back up to permutation and look at the definition. And it says, an arrangement of objects where order is important. Arrangement is a key word for us to know that we'll be using the permutation formula. But the most important thing about a permutation is that order is important. And again, we'll look at examples of how we know when it's a permutation. For a combination, a key word is selection. And with a combination, order is not important. So if we look at our first example, how many ways can you arrange 5 books on a bookshelf? So let's say you had one book that was a math book, another book was an English book, you had a science book, a history book, and a psychology book. You can arrange the books in this order on the shelf: math, English, science, history, psychology. But you could also reverse the order to psychology, history, science, English, and math. That's a completely different arrangement. Or you could completely mix it up all together and have English, then psychology, then math, then history, and then science. So you could write out all the possible orders But since the different arrangements would look different on the shelf, that's what makes this a permutation. So this one is a permutation. So we're going to use the NPR formula. So now that we know that we're using a permutation because the order matters, the formula is n factorial over n minus r factorial. So the most difficult part about permutations and combinations is figuring out which one it is. So if you're arranging books on a shelf, changing the order would give you a different arrangement of books. So we want to figure out what is our n and what is our r. So n is always your total. We have 5 total books that we want to arrange. Since we're arranging all of them, our r is equal to 5. So if we take these values and substitute them in the formula, we have 5 factorial over 5 minus 5, which is 0 factorial, and 5 factorial is 5 multiplied all the way down to 1, and 0 factorial, by definition, is 1. So our 1's cancel, and we're left with 5 times 4 times 3 times 2, and if we multiply 5 times 4 times 3 times 2, we get 120. So we have 120 different ways that we could arrange the books on a bookshelf. Now number 2 is very similar. We want to now arrange 10 books on a bookshelf, but we only have room for 3. So if we only have room for 3, then using the permutation formula again, because when you put the books on a bookshelf, you are arranging them, that makes it a permutation. Your n is equal to 10 because you have 10 to choose from, but you only have room for 3, so your r is equal to 3. So now that you've identified your n and r, and we know it's a permutation because it's an arrangement, the formula is n factorial over n minus r factorial. So we have 10 factorial over 10 minus 3, which is 7 factorial, and I take 10 and I multiply it down, but I stop at 7 because I have a 7 in the denominator, and the 7 factorials cancel, so that I'm just left with 10 times 9 times 8. And 10 times 9 times 8 is equal to 720. So for number 3, how many different ways can 4 adults be seated in a car? So if I draw a car, and I have 4 people are to be seated in a car. This one right here is the driver's seat. If we have 4 people, let's label those people A, B, C, and D. So we could have person A driving, person B in the passenger seat, C behind the driver, and D behind the passenger in the front. That's one arrangement. Another way that they could be seated is we could switch the people in the front seat, here's the driver, to person B driving, person A is the passenger. We could keep the people in the back or switch the people in the back, but this is a different way that the people could be seated. So we don't have the word arrangement in the problem, but how many different ways is another way of saying how many different arrangements. That's what makes this problem a permutation. So this problem is a permutation, so we'll be using NPR. The formula is n factorial over n minus r factorial. And we have 4 adults that are to be seated. So we have 4 people to choose from, so n is 4. We're seating all 4 of them, so r is also equal to 4. So we take the numbers and plug them in, and we end up with 4 factorial over n minus r. N minus r is 0. So I multiply at the numerator, and 0 factorial by definition is equal to 1. The 1's cancel, and I'm left with 4 times 3 times 2, which is equal to 24. So you have 24 different ways that the 4 people could be seated in the car. Now for number 4, how many different ways can 3 adults and 1 child be seated in a car? This problem is also a permutation because when we change the way the people are seated, we have a different arrangement of people in the car. This problem, though, I'm not going to solve by a permutation. I'm going to solve it using the counting principle. So if I draw the car, and I have the 4 different seats. This dot here is the driver's seat, and I have 3 adults and 1 child. The difference between this problem and number 3 is that you don't have 4 people that could be seated in the driver's seat because you only have 3 adults. So if you have 3 adults, you have 3 choices of people who could sit in the driver's seat. The next problem is that when we get to the passenger seat, we have 1 person that's been selected to drive and 3 people left to be seated in the car. The child cannot sit in the passenger seat, so we have 2 remaining adults that could sit in the passenger seat. When we get to the back seat, we have 2 people left that are to be seated, the 1 remaining adult and the child. So 2 people could sit here, that could be the adult or the child, and 1 person is left to sit at the end. So instead of doing this as a permutation, which would be a little bit more difficult, we're going to do this as the counting principle and multiply those 4 numbers together. 3 times 2 times 2 times 1 is equal to 12. And the reason why I'm doing this problem as a counting principle is because sometimes there are problems worded this way in a permutation assignment, and it is much simpler to solve it as a counting principle problem. So for number 5, we have 3 couples are to be seated in a row of 6 chairs. So 3 couples means that we have 6 people. So we have 6 people and 6 chairs. How many different ways can they be seated? So this is a permutation, because if we change the order of people, we have a different arrangement. So different ways is like different arrangements. So this is a permutation. So if we have a permutation, we have NPR. Our N is equal to 6 because we have 6 chairs, and our R is equal to 6 because we're seating all 6 people. So if we substitute it in the formula, n factorial over n minus r factorial, I have 6 factorial over 6 minus 6, which is 0 factorial, and if I multiply out the numerator, the denominator is 0 factorial, which is equal to 1, and I'm left with 6 times 5 times 4 times 3 times 2 is equal to 720. So there are 720 different ways that 3 couples could be seated in a row of chairs. Now this problem I'm also going to do by the counting principle, just so you can see the options. If I have 6 chairs, I'm going to draw out 6 spaces, one for each of those 6 chairs. So if you have 6 people that are to be seated, any of the 6 people could sit in this first chair. So whoever sat here cannot sit in the rest of the chairs, so you have 5 people left that can sit in the second chair, then 4, then 3, then 2, and then 1. Multiply these all together and you get 720. So this problem is definitely shorter by the counting principle, but just so you can see 2 ways, it's also done as a permutation. For problem 6, it's similar to problem 5, but we have 3 couples are to be seated in a row of 6 chairs. So once again, 3 couples is 6 people. But in this one, you have how many different ways can they be seated if each couple must sit together. This problem is much easier to do as a counting principle problem. So if you see it in a permutation section, you'll find it easier to do as a counting principle. So I'm going to make 6 spaces for 6 chairs. And in the first chair, any of the 6 people can sit in that first chair. Since couples have to sit together, the person who came with the one who sat in the first chair has to sit next to him, so there's only one person that could sit next to him. That means there are 4 people left. Any of the 4 people can sit in the third chair, but his partner has to sit next to him. So the 2 people that are left, any of the 2 people can sit here. With only one person remaining, we have 6 times 1 times 4 times 1 times 2 times 1 is equal to 48. So there are 48 different ways that the people could be seated. So with number 7, Faith has room in her bag for only 3 books. If she has 5 to choose from, how many different selections of books can she choose? Now this problem is not a permutation. This is a combination. We have how many different selections? So let's say she has 5 to choose from. So let's use the same books that we used in example 1. We have a math book, an English book, science, history, and psychology. If she were to choose the math, English, and science book to take with her, it doesn't matter the order that she chooses the books in, they're going to be placed in her bag. So since the order that she places them in the bag doesn't matter, this is a combination. So in a combination, we have NCR, and the formula is n factorial over r factorial, and then times the difference of n minus r factorial. So our n is how many books we have to choose from, which is 5. So our n is equal to 5. Our r is how many that we're actually choosing, which is 3. So n is 5 and r is 3. So n factorial is 5 factorial. R factorial is 3 factorial. And then we take the difference between those two numbers, which is 2. Starting with our 5, we multiply down and stop at 3 factorial because 3 is the larger number in the denominator, and we expand the smaller number so that the 3 factorials cancel. And we have 5 times 4 over 2 times 1, and 20 over 2 is equal to 10. So she has 10 different selections of books. Now before I scroll down, if we take a look at number 8, the only difference between number 7 and number 8 is that now she's only taking 2 books. She still has 5 to choose from. How many different selections of can she choose? So if I write those same books, math, English, science, history, and psychology, if she's choosing the English and science books this time, she can either choose English then science or science then English. Either way, she's taking the English and science books. So how many different selections means that we have a combination? So NCR is equal to n factorial over r factorial, and then n minus r factorial. And our n is how many books she has to choose from, which is 5. Our r is how many books she's taking, which is only 2. So plugging these numbers in the formula, we have 5 factorial over 2 factorial, and then if we subtract 5 and 2, we get 3 factorial. So this looks the same as problem 7. I start with 5 and multiply down until I stop at 3, because 3 is the larger number in the denominator. So I expand the smaller one, cancel the 3's, and I'm left with 20 over 2. So this comes out the same because, I'll scroll back up, in number 8 we were taking 2 books, but in number 7 we were taking 3 books. Both were from a selection of 5 books, and since the sum of two numbers is the total selection, that's why they both came out to 10. For number 9, a teacher selects 4 students to be on a committee to represent a class of 20 students. How many different committees are possible? So if we had 20 people, and we want these 4 people to be on the committee, person A, person B, person C, and person D. It doesn't matter the order that I choose these 4 people in. I can choose them in the order A, B, C, D, or I could choose them in the order B, A, D, C, or I could choose them in the order of D, A, B, C. Whichever order I choose them in, I have the same committee. So rather than writing them out, once I recognize that the order that I choose these people in doesn't matter, it makes it a combination. So I use NCR, n factorial over r factorial times the difference of n minus r factorial. And my n is how many people I have to choose from. This is a class of 20 students, so n is equal to 20. My r is the size of my committee, how many people I'm actually choosing, which is 4. So when I substitute in the numbers, I have 20 factorial over 4 factorial, and then the difference is 16 factorial. So for 20 factorial, I multiply 20 times 19 times 18 times 17, and I stop at 16 factorial because 16 factorial is the larger number in the denominator. The smaller number is 4, and that's the one that I expand. The smaller number is 4, so that's the one that I expand. The 16's cancel, and then I have 3 times 2 times 1 is 6, which cancels with the 18 to make it a 3. The 4 cancels with the 20 to make it a 5. So you can just multiply the numerator and denominator out, or you can look for numbers to reduce to make your multiplication easier, especially if you don't have a calculator. 5 times 19 times 3 times 17 multiply these numbers together, and I get 4,845. So you have 4,845 different committees that can be formed from a class of 20 students. For number 10, Nicholas is choosing toppings for a pizza. He can choose 4 meat and 5 vegetable toppings. For part A, how many pizzas having 1 meat and 2 different vegetable toppings can he choose? So in this example, this is a combination because it doesn't matter of the order that he puts the meat and vegetables on the pizza will have the toppings that he chooses. So we are choosing 1 meat from a selection of 4 possible meats. We are choosing 2 vegetables from a selection of 5 different vegetable toppings. So we want to take the combination of our meats and multiply it times the number of combination of our vegetables. So for our meats, we have 4 possible meats, so n is equal to 4, but we're only choosing 1, so r is equal to 1. For our vegetables, we have 5 possible vegetables to choose from, so n is equal to 5, but we only want 2, so our r is equal to 2. So using our formula for meat, we have 4 factorial over 1 factorial, and then the difference between 4 and 1 is 3 factorial. For our vegetables, we take our n, which is 5 factorial, over our r is 2 factorial, multiply it by the difference is 3 factorial, and I expand each of these fractions out. So 4 times 3 factorial over 1 times 3 factorial, and then for the second fraction, I stop at 3 factorial, and the 3 factorials in the first fraction cancel, so that I'm just left with 4. The 3 factorials in the second fraction cancel, so I'm left with 20 over 2, which is 4 times 10, and we have a total of 40 different pizzas that he can make by choosing 1 meat and 2 vegetables. For part B, now he's choosing 2 different meats and only 1 vegetable. So we had a selection of 4 possible meats and 5 possible vegetables. So this is another combination of meats and vegetables, so we multiply them together. Our n for meats are equal to 4. Our r is 2 because we're only choosing 2. For our vegetables, we can choose from a selection of 5 different vegetables, but we only want 1, so our r is equal to 1. So using our combination formula for meats, we have 4 factorial over 2 factorial, then we subtract the two numbers is another 2 factorial, multiply it by the combination formula for vegetables, which is 5 factorial over 1 factorial, and then the difference between 5 and 1 is 4 factorial. So 4 factorial is 4 times 3. I stop at 2 factorial, and I just have to expand one of them out in the denominator. And now for vegetables, I stop at 4 factorial. 1 factorial is just 1. And then I cancel. So the 2 factorials cancel. So with my meat, I'm left with 12 over 2. And the vegetables, the 4 factorials cancel. I'm just left with 5. So 6 times 5 is equal to 30. So for part B, there are only 30 different pizza selections that he can choose. For part C, how many pizzas having 3 different toppings can he choose? So we know from the beginning that he has 4 different meats and 5 different vegetable toppings. So if we just want 3 different toppings, they could all be vegetable, they could all be meat, or they can be any combination of meat and vegetables. So therefore, we have a total of 9 different toppings. So this is still a combination because it doesn't matter the order that he puts the toppings on the pizza. Our n is equal to 9 because we have 9 toppings to choose from, but we're only picking 3, so our r is 3. So using the combination formula, we have 9 factorial over 3 factorial, and then we take the difference between 9 and 3. We expand the numerator, stopping at 6, because 6 is the larger number in the denominator, and we take the smaller number and expand it to 3 times 2 times 1. The 6's cancel. The 2 and 1 reduce with the 8 and make it a 4. The 3 cancels with the 9 to make it a 3, so that we have 3 times 4 times 7, and 3 times 4 times 7 is equal to 84. So if he could choose any 3 toppings, he has 84 different possible pizzas that he could make.